All right, so today we're going to be finishing up chapter 14, our discussion of solutions, and we're going to be talking about what are called colligative properties. All right, and that term colligative refers to properties that depend only on the number of particles that are dissolved in a particular solution. Okay, so basically these are going to be how pure substances, for example, pure water, differs from water that's now had like sodium chloride or some other solute added to it, right? So we're going to be talking about three different types here of colligative properties. The first one is what's called vapor pressure. Okay, and so you may have heard of vapor pressure before with regard to pure substances. So again, now we're going to compare solutions versus pure substances. Strictly speaking, vapor pressure is the pressure of the vapor being given off by a particular liquid, right? So it turns out that any liquid has some amount of molecules that are escaping into the gas phase, all right? And the pressure that's emitted by those molecules is constant, okay? So okay, and kind of how you can think about vapor pressure is it's the tendency of a molecule that's in the liquid phase to kind of break free and escape into the gas phase. Okay. All right, and so compared to a pure substance, a solution always has a lower vapor pressure than that pure substance. Okay, we call it a vapor pressure depression. Vapor pressure depression. Okay, but so solutions have a smaller vapor pressure than the pure substance, than the pure solvent, let's say. Okay? You can sort of quantify this using this formula here where the vapor pressure of the solution is equal to the mole fraction of solvent in solution times the vapor pressure of the pure solvent. Okay, so this is going to give us an opportunity to practice our mole fraction as well. So let's take this part by part. Let's first practice getting our mole fractions here. All right, so given that we have 3 moles of sodium chloride combined with 55 moles of water, give me what the mole fraction of sodium chloride is. Get out my calculator too. All right, so let me actually take this to a new page. So remember, the mole fraction of NaCl is going to be the number of moles of NaCl divided by moles total, which is, in this case, moles solute plus moles solvent, right? That's how I get the total number of moles. So in this case, it's my 3.0 moles NaCl over the 3.0 plus the 55 moles of H2O. Okay, so that means my mole fraction of sodium chloride in this solution is 0.0517. All right, because this is I told you that because this is a mixture of like addition and multiplication, I'll just tell you to round it to 3 sig figs or something. We don't have to be really good about our sig figs with these mixed things. It's kind of a pain in the butt. I don't feel like going down that whole rabbit hole, all right? Anyways, mole fraction, meaning moles of sodium chloride divided by the total number of moles, which is again going to be solute plus solvent. All right, so now we can use this new bit of information that we learned. Let's say if H2O has a vapor pressure of 0.013 atm, what is the vapor pressure of this solution? All right, and again, we're going to need to use that new formula that we just learned about, where the vapor pressure of the solution is the mole fraction of solvent times the vapor pressure of the pure solvent. Okay, now, importantly, is this 0.0517, is that the mole fraction of my solvent in my solution? No, it's the mole fraction of the solute, the sodium chloride, right? And that is by far the most normal way to talk about concentrations, is in terms of how much solute there is. But if we look carefully at our equation here, I need to know the mole fraction of the solvent. Okay? The good news is that there's this very simple relationship between the mole fraction of the solute and the solvent, because they both have to add up to what? 1. Right? That would just be the total number of moles. You could also do it the long way, 55 divided by 3 plus 55. Or we can just note that the mole fraction of the solute plus the mole fraction of the solvent will always equal 1. Right? So in that sense, it's much easier to find the mole fraction of the solvent, given that I have it for the solute. So my P solution, that's 1 minus that 0.0517 value we just calculated, times the vapor pressure of the pure solvent, the vapor pressure of pure water, which is that 0.013 atm. All right, so punch that into my calculator. First of all, should I get a bigger number or a littler number than that 0.013 atm? Littler number, because the vapor pressure of a solution is always less than that of a pure solvent. Right? This is one of these amazing things about these colligative properties, is that they're uniform across the board. It actually doesn't matter whether it was sodium chloride or sucrose or whatever it is in there. Just having any amount of solute dissolved in your solution will lower the vapor pressure. So indeed, I get a littler number, 0.0123. We'll keep it at 3 sig figs. And then what should my units be? We're talking about a pressure, so ATM. All right. All right, so then the next one we're going to talk about. So vapor pressure, we're going to talk about freezing point. And this is, of course, the temperature at which a liquid solidifies. All right, likewise, again, we're going to have this across the board. The freezing point of a solution is always less than that of a pure substance. Okay. Likewise, we have an equation that sort of governs this here. The change in temperature, right? And again, we just have to remember that it's always going down, okay, is going to be equal to the, what does the fancy cursive lowercase m stand for? The molality of that solution times this constant here. All right, and the constant is going to be unique for every particular solvent. Okay, and so we can just note that these are tabulated in these tables here, so we can see for different solvents that Kf value will vary. Right? And so we'd have to know for our particular solvent, we'd then go look on the table in order to identify a specific value here. So if we're talking about an aqueous solution, we would look at water. and have to look up its Kf value here. All right, so what type of problem can we do here? So again, let's just use this as an opportunity to practice our molalities here. So all right, so if 0.65 moles of sucrose were combined with 500 kilograms of water, take a second and tell me the molality of that solution. Oh wait, no, not 500 kilograms. That'd be ridiculous. 500 grams. My bad, that would be like throwing a cube of sugar into the ocean. All right, so our definition of molality was moles of solute over kilograms solvent. Okay, 500 grams is how many kilograms? 0.5. And then I'll be good with my sig figs, keeping all those zeros on there. All right, so what, 1.3? So 1.3 molal solution of sucrose. Okay, so that would have been concentration stuff, what we discussed last class. Now we can tack on this new concept that we learned about freezing point depression, and I can ask something along the lines of, what is the freezing point? Of this solution? Okay, so how are we going to use our little chart here? So first of all, we can just note the equation was, again, change in temperature equals the molality times that constant value. I'm going to look it up for my particular solvent, which is in this case water, right? Because I added sucrose to water. So I'll go to my table here, look under water, and note that that Kf value is 1.86. All right, so then the change in temperature is going to be that 1.3 molal solution times that Kf of 1.86. We see the units up here, it's degrees Celsius per molal, so that cancels out my little fancy m. All right, and then multiply that together. Get 2.418. My units are degrees Celsius, right? Because molal has canceled. And then how many sig figs? 2. Okay. So then am I done? because let's be clear, the question was, what is the freezing point? Right? So what I've calculated here is, what does this delta mean? Change. So I've calculated how much it's going to change from what it normally is, all right? But I have to make note, water normally freezes at 0 degrees Celsius, okay? If I make a solution, is it going to freeze at a higher or lower temperature than 0? Lower, always lower, right? Freezing point depression. So this delta T, these K values are reported as positive numbers. You could have easily made them negative numbers and then it would have made sense. Anyways, they're always reported as positive values. We have to know that it goes down by that much, right? So if I want to know the temperature that this solution is going to freeze at, I have to start at my normal freezing point and subtract that delta TF. That's what we just calculated, is the difference between your normal freezing point and now the freezing point of the solution, okay? So just be careful. You don't stop at the delta T. There's one more step, which is to take your normal freezing point and subtract that delta TF. All right, so T freezing minus the delta TF. That's my new freezing point. Okay, so in the case of water, all right, so in this case it would be negative 2.4 degrees Celsius. Okay? All right, and we're talking about freezing. Now we're going to talk about the other direction, the boiling point. This is the temp which a liquid goes to the gas phase. All right, and the freezing point of a solution is always less than that of a pure substance. The boiling point of a solution is always more than that of a pure substance. So the boiling point of a solution is greater than a pure substance. Okay, and we have a very similar equation that sort of relates these. The delta T of boiling is again equal to that molality times yet another constant, Kb. All right, so now let's take this same sort of thing. We'll work with this same solution since we already went through the trouble of calculating its molality. And now I want to know what is the boiling point of this solution. All right, so again, we're going to have to go to our chart. We're going to have to look up for our particular solvent. What is the solvent that we're using in this case? Still water. So I'm going to find water on my chart. We saw that over on the left-hand side was these Kf values that were listed. That's what we used previously. And we see that on the right-hand side, we have our Kb values listed. Okay, so if you want to calculate the boiling point of this solution, you're going to need to use that Kb value for water. Everybody take a second and see if you can't get me the boiling point of this solution based on what we discussed before. It's going to be an analogous problem. What's up? Yeah, we're going to stick to this same solution since we already went through the trouble of calculating its molality. All right, you can give me your answer to 2 decimal places, let's say. All right, so I got my delta TB equals that molality times Kb. My molality of my solution was that 1.3 molal. Okay, and then I'm going to multiply that by the Kb specific for my solvent. Again, we were talking about water, so I'm going to use that 0.0512. Again, the units are degrees Celsius per molal. These cancel out, leaving me with a delta TB of 0.6656 degrees Celsius. Again, I said we could do 2 decimal places. Okay, and then I'm done? No, because of course this solution is not going to boil at 0.6 degrees Celsius. That's the difference between the normal boiling point and the boiling point of my solution. And again, is this boiling point going to go up or down? Up for boiling, down for freezing, up for boiling, right? So that means in order to calculate my new boiling point, I'm going to take the boiling point and add that delta TB on there. You can see that the freezing and boiling points are listed for each solvent. I mean, I think for water, we probably know it, but if it was any other solvent, right, that information is just here on the table. For water, normal boiling point is 100 degrees Celsius. So this is TB solution. So I'm going to take my 100 and add that value there. All right, again, I just said 2 decimal places to make it easy. So 100.67 degrees Celsius. That's my new boiling point of my solution. All right. So before we move on, let's just take a second to kind of like think about these a little bit more qualitatively, not quantitatively. But we said that freezing point is less than that of a pure substance. We had this equation. But now let's sort of think about why. All right, because again, one of these things about a colligative property is it doesn't matter whether you're dissolving sugar or salt or whatever. We never factored in the identity of the solute into any of this, right? It's just unique, or it's a property that depends only on the number of particles that are dissolved in that solution. So why across the board do freezing points decrease for solutions compared to pure solvents? Okay, so the reason is because, and actually we could sort of use an example from like the real world here. there are certain parts of the world, up north, North Pole, where the ocean will actually freeze in the winter, right? We get this ice that's produced from the ocean. The ice that you get, if you were to take it out and pop it in your mouth, it's not salt water anymore, right? When the ocean freezes, it freezes as pure water, which means that those water molecules have to push those sodium chloride molecules out before they solidify and freeze together, okay? So this process is called like exclusion. Basically, the solvent, before it can actually solidify, has to exclude those solute molecules, which requires more energy, which is why it has to be a lower temperature than it normally would, right? So why is freezing point depressed? Because the solvent excludes solute particles before freezing. Before solidifying, let's say. Make it fancier. Okay? And then this also sort of explains, well, then that's why if I have an even more concentrated solution, a higher molality, I have to go even lower of a temperature, right? Because then I have that many more solute molecules. I try to get out before I can actually solidify. Okay. So then boiling point. Why is boiling point going to be greater for a solution than it is for a pure substance? So again, we can think about why. Okay. So first of all, why does something boil? Like, what is the boiling point? So boiling point means that the vapor pressure equals the atmospheric pressure. Right? So, I mean, you don't have to be a chef to have boiled a pot of water in your life, right? What happens when you boil water? What do you see? You see water vapor, and specifically what are we seeing as it's boiling? Bubbles, right? So how is a bubble forming? And the bubbles tend to form from the very bottom, right? And then rise to the top. So how do we have a bubble, something getting to the gas phase at the bottom? It's because the vapor pressure of that solution is now equal to the atmospheric pressure. That's the point at which a solution boils, okay? Which means that if we were to go up into the mountains, right, where the atmospheric pressure is lower, right, our boiling point changes, because it really depends about just the atmospheric pressure. So then why, if I have a solution, is the boiling point going to be higher? Because remember, what happens to the vapor pressure of my solution as I start adding solute? It goes down. So now I have to go to a higher vapor pressure, a higher temperature to get that vapor pressure equal to the atmospheric pressure, okay? It's a little bit less intuitive than the freezing explanation, but yes, vapor pressure has to equal atmospheric pressure at the boiling point, and vapor pressure of a solution is less than a pure substance. What's up?
So why does the vapor pressure go down then?
The vapor pressure, yeah, so we could do that one as well. All right, so then why vapor pressure decreases? Okay, we can sort of look at this one pictorially. Whoa. Here's going to be my pure substance. Here's my my solution, rather. All right, so my pure substance is obviously just pure solvent. When I make a solution, now I got these solute particles that are dissolved there, right? And really the key here is what's happening at the very surface, right? Again, your vapor pressure is where your liquid phase is escaping into the gas phase, right? Well, if you have fewer particles on the surface, a smaller fraction of them are going to escape into the gas phase. So it's really just a fact that you have space occupied by those solute molecules solute particles at the surface, right? If you're going to say 90% of, that's a huge number, so let's not say that. 5% of the molecules at the very surface are going to escape, right? Well, if there are just fewer of them up there because there's a bunch of solutes occupying that space, then 5% of a smaller number is a smaller number, right? So bottom line is why? Because there are fewer solvent particles at the surface in a solution. All right. Now, with regard to our problems involving freezing and boiling point, I conveniently use this sucrose solution, right? Meaning a non-ionic compound, a non-electrolyte solution, okay? Let's remember, for ionic compounds, when they're dissolved into water, what happens? Right? If I take sodium chloride and dissolve it in water, what happens to that ionic bond? They dissociate, right? So I actually have sodium ions floating around independently from chloride ions, right? So let's just remember, when ionic compounds dissolve in solution, they dissociate into cations and anions. All right, so if I start out with 1 mole of sodium chloride, how many moles of ions do I have when I create a sodium chloride solution? One mole NaCl dissociates into how many moles of sodium ions? 1. And then how many moles of chloride ions? 1. All right, so I actually have 2 moles of ions because of that dissociation. Okay? So what we're going to do is, and if you had looked on our constants page, you'd see that the formula for freezing and boiling depression is slightly altered. Because what we're going to do is we're going to put this little factor out here, I. This is what's called a Van't Hoff factor. and accounts for the number of particles from a dissociated ionic compound. All right, same thing over here with our boiling point depression formula. Right, we're going to add that Van Hoff factor there. Okay, so for sodium chloride, what would we expect our Van Hoff factor to be? 2, right? So again, it's just the number of particles that you get, right? So we would expect it to be 2, okay? They've done a lot of experiments, and you would expect it to be 2, but actually a better value would be closer to 1.9, okay? So you can see that for certain compounds, what we would expect, we actually have a slightly different value when we measure it. Y is measured different than expected. Okay. Okay, and this is what's called this phenomenon of ion pairing, which just means that there's some small population of ions in solution at any given moment in time that are still bound together, still talking to one another, right? So out of all of those sodium chlorides floating around, sodium ions and chloride ions floating around, it turns out that about 5% of them are still talking to one another. You still have that chloride ion associated with that sodium ion because, of course, there's still that opposites attract interaction between the two of them, right? There's that ion dipole factor that's causing this mixing to occur. Water does favorably interact with the ions, but ions also favorably interact with one another, right? So both of these forces are in pull at one time, and so for a small population of ions in solution, they're still paired. They're still talking to their counterpart, right? So ion pairing, small fraction of oppositely charged ions paired together. Okay, so we'll have this Van Hoff table, and this will just help us get more accurate data, right? If you weren't given a Van Hoff factor, you could go off of what you would expect. Notice how it's pretty close, right? But we can just be more accurate if we use some of these measured tabulated Van Hoff factors rather than what we would just predict based on counting number of ions. Okay? And then notice, of course, for a non-electrolyte solution, that I is just 1, and that's how we get our original boiling point depression, boiling point elevation, freezing point depression formula back. Okay? Cool. All right, we're going to stop it there. One more thing.